Today we have a physics two-dimensional forces review. The basic idea when you have a force at an angle, no matter what the angle is to break it into components. You want to break into horizontal and vertical components that take the place of the original force. You can't add a force when it's off at some angle. We need our forces to be all lined up on the x-axis or lined up on the y-axis for us to be able to add them. So if you have a tension that's up and to the right, break that into the horizontal and vertical components. We use our knowledge of trigonometry. Cosine is adjacent over hypotenuse. In our case, the adjacent force is the x component. It is next to that theta. And the hypotenuse is the actual tension, so the actual tension in the rope. So rearranging that equation, you get that the horizontal component is just the hypotenuse, which would be the tension in the rope, times the cosine of theta. And in the vertical direction, sine theta is opposite over hypotenuse. If you substitute in our opposite, it would be ty, and the hypotenuse is the actual tension. Rearrange for the vertical component of the tension, ty, and you get t sine theta. This same approach works if we're in any quadrant. You just want to break your forces down into the horizontal and vertical components, with the horizontal component laying on the x-axis, either the positive or the negative x-axis, and the y component is just kind of out there on its own. This way, the horizontal component will always be cosine and the hypotenuse, and the vertical component will always be sine. The basic idea is, again, that you want to break the components, break any force that's not already in the x-axis direction or y-axis direction into those horizontal and vertical components, using trigonometry to do that. I like to draw them in a different color so that I can see that those are taking the place of the original. This way we can add the x forces together and then separately the y forces together. You can never add a horizontal force to a vertical force. There's no way that a force in the horizontal direction could do anything to the vertical direction. Treat them separately. Let's do an example problem. In this case, you have a 694 kilogram mass suspended by two ropes. We already know the angle. We want to know the tensions in the rope. So first we'll start by drawing a free body diagram for the knot. So this is for the knot that is combining those three ropes. We have tension in the rope that's actually attached to the mass, and then the two that are pinned to the wall. This object is in static equilibrium. That means that the sum of the forces is zero. There is no net force. It is a special case of no net force. It is not just not accelerating, it's not even moving. It's static, stationary. So T1 is the only one that we have to break into components. We know that it makes an angle of 40 degrees with the wall. You can see that the x-axis and that ceiling actually are parallel to each other, cut by a transversal that is T1. Alternate interior angles of two parallel lines are congruent, so if it's 40 degrees from the ceiling, it's going to be 40 degrees from the horizontal. And then, of course, we will sum our forces in the x direction and separately in the y direction. You look at your free body diagram to know what to put in for the sum of the forces. You do need to literally add them. So in the x direction you have T2 that is to the right, subtract off T1 that is to the left. The y direction you have T1 y component that's up minus T3 that's down. So we know the weight of this object. It is the mass times the acceleration due to gravity, 694 times 10. We're using a positive 10 because we're just trying to find the weight. It's not in a motion equation. If the weight is 6,940 newtons, then T3 must also be 6,940 newtons. That's essentially a free body diagram of the mass. Then we can put in our numbers. For T1x is T1 cosine 40, and T1y is T1 sine 40 from the same reasoning as the previous slide. This gives us enough information to solve for T1. We get an actual number for T1 from our vertical sum of the forces. and then you use that number in to find T2. You could be asked to solve for just the horizontal component or just the vertical component, just T1, just T2, but your free body diagram and sum of the forces is the key for any of those. Notice that the weight of the object is 6,940 newtons, but the tensions in the ropes are greater than that. It requires more force than 6,940 newtons for tension in those ropes because they are acting at an angle. Not all of T1 is working to support the mass. Some of it is just working to balance out T2. So the actual tension T1 is greater than the weight that it's supporting. But its vertical component is equal to the weight. Another problem. This was a homework problem. Rescue worker pulls an injured skier. You know the lengths of the ropes here. We know the mass of the skier on the toboggan, 127 kilograms. You know that there is a tension of 148 in the rope. You're actually asked to solve for the coefficient of friction in this problem. First, you're just going to use those distances, those lengths, to find theta. That's the only thing you can do with those. The length of the rope tells you nothing about the tension, but it does tell you about the angle. So if it's 1.65 meters above the ground, then that's opposite, and hypotenuse is, because you draw a picture, you see 2.43 meter long rope. When you are solving for an angle, that's when you use inverse sign, second sign, shift sign, and you get that angle is 42.8. So we already know that tension is at the angle, so you draw that in first, try and make it realistic, a little less than 45. We can also solve for the weight, so we know about how long to draw that vector, the mass times acceleration due to gravity, 1,270 newtons. We also have friction that opposes the motion. Friction always opposes the motion. We're making the skier get pulled to the right. Friction will oppose that motion and be to the left. We have one more force we need to put on, which is normal force. Before we do any calculations, we know that normal force is going to be less than the weight. If normal force was equal to the weight in this problem, then your skier would jump up off of the ground, or the toboggan would jump up off of the ground, because you would end up with an overall force upward. That's not going to happen. Normal force is a passive force. It will just be what it needs to be so that the sum of the forces is zero. Normal force will never cause an object to accelerate. So your up forces have to balance your down forces. Tension has a component that is up. So normal force does not need to be as great as weight for the up forces to balance the down forces. Look on that free body diagram. There are two up forces. Normal force that is completely in the up direction, and then tension that has a component, a part of it in the up direction. Add those together to balance out the weight. After you have a free body diagram, the next step is always sum of the forces in the x equals ma, sum of the forces in the y equals ma. Use your free body diagram to put those forces in. There's where we're breaking tension into its horizontal and vertical components. The horizontal direction, you have Tx that is in the positive direction, subtract off friction, equals 0. Normal force up, the y component of tension up, subtract off weight, equals 0. And then we'll see where we get stuck. That's usually the next step, is you substitute things in. If we're solving for mu, instead of writing friction, substitute in mu times the normal force. Solve for, we would need to solve for normal force because we don't already know it, and there's no way you can get mu unless you know normal force. Your vertical sum of the forces is what lets you get normal force. Weight minus Ty, substitute in your values, and you get that the normal force is 1,169 newtons, which is in fact less than the weight. The weight was 1,270 newtons. And you can take that answer and substitute it in for normal force in your other force balance. And solve for mu, and you get a pretty small number for mu, which is what you would expect if you're sliding across snow. another example problem. In this case, we have a crate sliding down an inclined plane. These are a little bit different. You are still have forces at angles, but this is the only time that we will tilt the axes. We tilt the axes so that the x direction, the x-axis, is in the up and down the hill direction, and then the y-axis, it would be the same direction as your normal force, always perpendicular to the x component. So we know the mass of the crate that's sliding down a ramp. We know the coefficient of friction, and we're actually going to solve for the acceleration of the crate. You're not told that it's at constant velocity. If you're not told constant velocity, you can't assume that. So draw a picture always so you can visualize what's happening, and then free body diagram. You have the weight is always pointing straight down. Notice our axes. That x-axis is parallel to the ramp. The ramp and the x-axis are equal distance apart. They are parallel. The x-axis is at the same angle as the ramp. The y-axis is perpendicular to the x-axis. They make a 90-degree angle with each other. Weight is not on either one of those axes. Normal force is perpendicular to the surfaces in contact. Normal force is going to be on the y-axis. It has to be because the x-axis is in the direction of the ramp, which is the direction of the two surfaces in contact. Normal force is perpendicular to that. It is not straight up and down. It is not directly opposite the weight. Look at normal force and weight. They are not opposite of each other. They are not pointing in the same direction for an inclined plane. Friction opposes the motion. If crate is sliding down the ramp, friction points up the ramp. The angle, this is a reason that we break weight down funny for these. If it's a 20-degree ramp, then that angle between the y-axis and your weight vector is also 20 degrees. Weight is the one that we break into components. That vertical component of the weight is right on the y-axis. In this case, this is the only time we do this. The x component is the one that's out on its own. Let's sum our forces in the x direction and the y direction. Even if we're not sure what we're doing, we are absolutely sure that we're going to have to sum the forces. It'll get you started. We have the x component of the weight is pointing down the ramp. It's opposed by friction, so Wx minus friction equals ma. If we were told it was constant velocity, then we would put 0 over on the right side. If we're not told then we have to assume it's accelerating. In the y direction, we just have the normal force in the positive y. We're going to subtract off the y component of the weight. So if this is a 21 kilogram crate, that means it weighs 210 newtons. Nowhere in either of these equations will the number 210 be all by itself. The actual weight does not appear anywhere, just the x component and the y component. Those are not equal to 210. So our normal force is equal to not 210, but 210 times the cosine of theta. We have enough information that we can solve for the actual normal force. There's the 210 times the cosine of theta. Again, 210 is nowhere in there, just by itself. There is no 210 force. Normal force is 197. We have Wx minus friction, so that is the horizontal component, which is going to be sine because that horizontal component is opposite the 20 degrees. Minus mu times the normal force equals ma. You have enough information to substitute in for everything there except for acceleration. The horizontal component of the weight and friction are not equal to each other. If they were, there would be no acceleration, but in this problem they're not. So you know all of those numbers. That whole left side you can type in your calculator in one line, then divide by hit equals, then divide by 21, and you would get that the acceleration is 0.61 meters per second squared. That is a positive value for acceleration. That would mean that it's accelerating in the positive x direction. That means that it is accelerating down the ramp. In other words, friction is not big enough to make it stop. It is going to accelerate down the hill until it runs out of ramp. So basic types of problems, you have just forces at angles breaking into components. You have a force at an angle for an object that's moving along the floor, moving in the horizontal direction. And then you have this type of problem where you have inclined plane. This is the only time that we tilt the axes, is when you have a ramp. And that's just so that when we find that acceleration, it's in the x direction, which is the down the ramp direction. Reworking these problems, just rewind until you get to just the original problem statement and rework these problems without looking at the work that's on here is a great way to study and reinforce your understanding.